This presentation introduces the transformative model architecture known as the transformer, which leverages attention mechanisms to improve translation tasks and other sequence processes. Traditional sequence transduction models like RNNS and LSTM have limitations in parallelization and computation time. The transformer model addresses these issues by using a novel attention mechanism, which allows for more parallelization and reduces training time significantly. This slide provides a visual overview of the transformer model. It shows the encoder-decoder structure with self-attention and point-wise feed-forward networks, aiming to process inputs and outputs simultaneously for better efficiency. This slide explains the two types of attention mechanisms used in the transformer. Scaled-product attention helps in dealing with different positions of a single sequence. Multi-head attention allows the model to focus on different positions at different representation subspaces. Attention mechanisms in the transformer are used in multiple ways. Encoder-decoder attention allows each position in the encoder to attend to all positions in the previous layer of the encoder. Self-attention, on the other hand, lets each position in the decoder attend to all positions up to and including that position. Each layer in the transformer's encoder and decoder contains a position-wise feed-forward network. This network applies two linear transformations with ReLU activation in the middle separately and identically for each position. Embeddings in the transformer model are used to convert input tokens into high-dimensional space vectors, and softmax is employed to convert the decoder output into predicted next token probabilities. Positional encodings are added to the input embeddings to provide the model with information about the order of the sequence. The transformer uses sine and cosine functions at different frequencies for this purpose. The self-attention mechanism is key to the transformer model's success. It reduces the overall computational complexity and allows for more efficient learning of long-range dependencies in the data. The transformer model was trained using a 2014 English-German dataset with 4.5 million sentence pairs and an English-French dataset with 36 million sentences. Training was performed on a machine with 8 NVIDIA bus. The base models trained for 100,000 steps for 12 hours, while the big models trained for 300,000 steps for 3.5 days. The Atom optimizer was utilized with EOS 0.9, and EOS 10.9, and a special learning rate schedule. Regularization techniques included residual dropout, label smoothing, and attention dropout to prevent overfitting and improve model performance. Various model configurations were evaluated to optimize the transformer's performance. These included adjustments to the number of attention heads, embedding sizes, and whether to use sinusoidal positional embeddings or learned positional embeddings. The results showed varying impacts on the model's BLE, U-score, and efficiency. The transformer's architecture was tested for its generalization capability on an English constituency parsing task. Using semi-supervised learning with the Penn-Treebink and Berkeley Parser Corpora that achieved BLE, U-score of 92.7, showing its robustness across different language processing tasks. The training costs for the transformer were compared to other models, highlighting its efficiency in terms of both performance, BLE score, and computational costs. The transformer achieved higher BLE, U scores while requiring significantly less training costs than previous state-of-the-art models. This slide offers a visualization of the transformer's attention mechanism, showing how different attention heads focus on various parts of a sentence to resolve long-distance dependencies, which is critical for understanding the meaning and context of a sentence. The transformer model has demonstrated superior performance in machine translation and other language processing tasks. Its ability to be trained more efficiently opens up possibilities for future applications in various input and output modalities beyond text, such as images and video. The attention patterns in the transformer provide insights into the model's inner workings. The encoder's self-attention layers learn to focus on different parts of the input sentence to perform various tasks. The provided visualizations illustrate how certain attention heads specialize in identifying sentence structure and relationships between words. This slide delves deeper into the attention details, showing how two different attention heads focus on specific word-to-word relationships within a sentence. The green lines highlight one head's attention pattern, while the red lines show another's, reflecting the diversity and focusing on sentence elements to capture the meaning effectively. The attention heads not only focus on individual word pairs but also exhibit behavior aligning with the overall sentence structure. Through attention visualization, we can see how the model learns syntactic and semantic patterns, which are crucial for tasks such as translation and sentence parsing.